Welcome, everyone. Thank you so much for joining us today for the Grasp on Robotics talk series. I am Kostas Daniilidis, and I'm the faculty host for today's talk. As a quick reminder, previously recorded talks can be found on our YouTube channel and website, and you will have the opportunity to ask questions at the end of the talk. If you have during the talk, please raise your hand and we will bring you the microphone. This is one of the most special Grasp on Robotics talks because I am very honored to host one of our very distinguished alumni, Nikolay Atanasov. I was very blessed to be his co-advisor together with George Papas, and I still remember the first day he actually joined when we started discussing and published our first paper together. Nikolay is now an associate professor at the University of California in San Diego. He obtained his bachelor from Trinity College in Connecticut, and his master's and PhD from Electrical and Systems Engineering here at Penn. His research focuses on robotics, control, and machine learning with emphasis on active perception. And for autonomous mobile robots, he works on probabilistic models and inference techniques for SLAM and optimal control and reinforcement learning for autonomous robot navigation and uncertainty minimization. He has received the Joseph and Rosalind Wolf Award for the best PhD dissertation at ESC, the best paper award at ICRA. Thank you, Nikolay. It's my only best paper award. And the NSF Career Award in 2021. And the IEEE Robotics and Automation Society in Early Academic Career Award in Robotics and Automation. I think any award that a young researcher can receive. Please, go ahead.
Thank you, Kostas. Hi, everyone. It's really great to be here. It's maybe one of the highest stakes presentations I'll be giving, because for me, it's kind of where it all began. That's when I first came here. I didn't know anything. I was a college student, and this place transformed me into a robotics researcher. So I'm also really excited to see everyone. So let me tell you a bit about how it all started. So here I am in 2009. Coming into Philly for the first time. You can see in front of the City Hall, having coffee at the Green Line in Clark Park. And then quickly after that, I went into the Grasp lab, and it was a lot of hard work. I was working with a PR2 robot, the Graspy. I hope it's still around and some of you use it. I spent a lot of time getting Graspy to move its hand around, and we were doing active perception with it, which led to my first journal paper in the Transactions on Robotics in 2014, where we had kind of object recognition with Graspy. So after 6 years of hard work and exciting experience, I made it. So you can see my defense there on the left. My thesis was called Active Information Acquisition with Mobile Robots. I managed to attract a crowd at my defense, which is a big achievement. And I'm very proud, and I was very lucky to get advice from George and Kostas. I learned quite a lot from them. It was time. So after the defense, it was time to open my wings and go far away and use my skills, go for a postdoc. So I went to Pennovation and got to work with VJ. We worked on the DARPA Fast Lightweight Autonomy project, and I learned a lot about aerial robots and drones. Maybe the most interesting work I worked on during the postdoc is this paper on the right. So we did search-based motion planning for quadrotors, and the main idea in that paper was that quadrotors are differentially flat, so you can map them into a kind of a linear system space, and then You can imagine using an A-star algorithm in the space of accelerations, velocities, and positions. And we observed that instead of a distance heuristic, now you can solve a linear quadratic minimum time problem in closed form. So this gives you a heuristic which respects sort of the acceleration, velocity, and so on. So that's a nice paper that I am still proud of. All right, so then what happened after? I moved to UC San Diego, so I'm going to speed up the timeline a bit. So I'm currently in Franklin Antonio Hall, which is a relatively new building. Now I have my own lab. It's on the 3rd floor. And we just recently got a Ricci 2 robot, which is kind of my new Graspy. It looks actually quite similar. So it's the new generation. This is my research group. So I have one postdoc, Brian, and the rest are my PhD students. Some are co-advised. And a lot of the work I'll talk about today is actually their achievements. So let's see what my lab does nowadays. So we're working on mobile robot autonomy, both aerial and ground. We work on multi-robot interaction and both localization, mapping, motion planning, control. I'd say we span the stack of autonomous robots. And very recently, we started to look into manipulation a bit. In a lot of my work in the past, I used to do only active perception, but never touching the world. So I've decided it's time to do some manipulation as well. So kind of the grand vision is to go after multi-robot mobile manipulation. Okay, so let's see where the state of the art is today in that sort of space. So nowadays, we have these model-free, large-scale policies that dominate robot autonomy. So on the left, you see an example of learning from demonstration. So this is work from Professor Xiaolong Wang at UCSD, where they have this open television system. Essentially, you teleoperate the robot and you receive some visual feedback. You collect a lot of demonstrations, and then you train behavior cloning policy to do dexterous manipulation on the left. On the right is an example of the physical intelligence policy, which I'm sure almost all of you are familiar with. So this is the Pi 0.6 VLA cleaning or making an espresso, cleaning the espresso machine. So this is again trained from a lot of demonstration with some reinforcement learning fine-tuning. So let's look a little more into this Pi 0.6. So this is what the Pi architecture looks like. So we give it 4 images and a language description of a task. And we extract tokens from the images and from the language, as well as some proprioceptive states in the robot. And these go as an input to a GEMMA, which is a vision language model. And from the GEMMA, we produce discretized actions. And finally, we have some sort of an action head, which does flow matching, diffusion sort of thing to predict the next action. So you can see it's kind of a one giant model, which takes images and the language command as an input and produces actions. And a lot of it is very black box. So we do kind of fine tuning afterwards. We formulate an RL problem where Pi is our policy here. There's a model of how things are changing over time, but we never know that, right? We only observe transitions from the observations from the images and from the robot states, and we never actually know this F function. The reward, there's probably some definition keeping it similar to the demonstrations. So yeah, so the policy is this VLA model I just mentioned. The reward is determined by language commands and demonstrations, and then the model is implicitly encoded by these transitions of states and actions. So in my talk, I'm going to look a lot closer into what the model is and how come we're kind of depending on this VLA model to understand implicitly what is going on in the model. So let's look more carefully. So there's actually a lot going on in the environment. The robot is moving around, so we have kind of robot dynamics. The environment is changing, and then finally the task that is given to the robot itself probably has stages. So for example, if you're making coffee, right, first you need to find the beans, then you need to insert them, you need to start the machine. So there's a sequence of states that the task is undergoing as well. So as a simple example, let's look at this kind of escaping a room example or door and key environment where you need to go to the green goal on the bottom right. but there's a door in the way. So if the door is locked, you need to grab a key. And if you have the key, you can unlock, otherwise you cannot, and then you can get out to the goal. So we can think of an environment model here, which describes the locations of start, goal, and key. We can think of the robot model, which is the red triangle, and how it's moving around. And we can think of a task model, which tells us, do I know where the key is? Do I have the key? Is the door open or closed? Am I at the goal? So maybe there are a few states for our task. Okay, so my work is quite model-based. So we're going to look at modeling for these three things. So how do we build robot models? How do we build environment models? And how do we build task models? And maybe eventually combine them into a complete system. Okay, so we're going to start with robot modeling. So in robot modeling, we are given a model of the system. So we have X is the robot state here, U is the input, and then F is the unknown dynamics of our robot. We're going to assume we have a data set of times, states, and inputs. And our goal is to estimate or construct an approximate model, F theta, that will approximate the actual dynamics. So we can formulate this as sort of a supervised learning problem, right, where the objective is to minimize the loss between the actual states and our predicted states. So X hat is what we can predict from the F theta model. And we're interested in minimizing this loss subject to the fact that the predictions come from the model. So we have something like this, right? The green curve here is the approximated trajectory from our model. The blue curve here is the ground truth we have from the data, and we're trying to minimize the error between these. So if we look at this problem in continuous time, right, if we have F theta as the neural network, for example, the first question is how to integrate F theta over time to get these state observations. So one of the very popular approaches for doing this is the neural ODE approach, which was a NeurIPS 2018 paper. They said that in that paper, they observed that you can use an ODE solver to produce the forward trajectory. So if you have F theta, you integrate forward in time. This gives you states at different discrete times. And then the only question is now, how do I find the derivative of this with respect to theta if I want to update my parameters? And in that paper, they observed, okay, we have the adjoint method, which is sort of Pontryagin maximum principle idea. I can formulate, so if I want to look at the derivative of the loss function with respect to theta, I can define an adjoint state, which is the derivative with respect to the state, derivative with respect to theta, and the state itself. There's some backwards dynamics, which tells us how these derivatives can be computed by solving another ODE, essentially going backwards in time. So the ODE network approach showed something like this. So first you compute the trajectory forward in time by solving an ODE. Then you formulate the adjoint states, and you compute another ODE backwards in time. This gives you gradients for theta, and you can update the parameter and repeat this again and again. So it's like back propagation, but through a continuous time model. So this is a completely black box. So in our work, we were interested in actually encoding some physics into this. So for example, we know that robot systems satisfy kinematic constraints, they conserve energy. So how can we capture this into the F theta model? So we know that all physical systems are actually Hamiltonian. So we looked at using Hamiltonian dynamics. So let me remind you very quickly what Hamiltonian dynamics are. So we have a configuration Q, we have a mass that might depend on Q, that's m by n, and we have a momentum, which is the mass times Q dot. So then we have the Hamiltonian, which is essentially the total energy of the system. So it's a combination of kinetic and potential energy. And then Hamilton's equations of motion tell us how the Q dot and P dot momentum dot and configuration dot evolve over time. And it's a matrix that looks like 0 identity minus identity 0 times the derivatives of the Hamiltonian with respect to the configuration and the momentum, and you can have some sort of an input. So the interesting or important part in the Hamiltonian dynamics is this matrix in red. It is always, it should be skew symmetric. So why is skew symmetric important? So if you ask how does the energy behave when the input is 0, so let's say I don't have any external forces into my system, then we have q dot by the chain rule, right, is dq, dh dq times q dot plus dh dp times p dot. We can use this relationship here to rewrite this as the gradient of H transpose times J, which is our skew symmetric matrix, times the gradient. And for a skew symmetric matrix, we know that X transpose AX is equal to 0. So as long as you have a skew symmetric matrix there, you guarantee energy conservation, which we know physical systems satisfy. Okay, so this is for Euclidean states. What if we have orientation? Like, for example, on a quadrotor system, we also have positions and we have orientations. So they might be on a manifold sort of domain. So we extended this, or we can formulate this Hamiltonian dynamics also on the space of rotations. So let's look at SE3, which is positions and orientation. So if we have a rigid body with position P, orientation R, and then linear and angular velocity, we can formulate this in a very similar way. So the configuration is the position and the rotation matrix is a single kind of stacked vector, so 12-dimensional. We have a 6x6 mass matrix. Again, we have the momentum is mass times the velocity. We have the Hamiltonian still, kinetic and potential energy. And we can write the Hamilton's equations of motion. So now, because we have a rotation matrix there, the J matrix is slightly different, but it's still skew symmetric. So the exact expressions look something like that. They have the R hat, which is the hat map of the cross product associated matrix shows up in here, but it's again skew symmetric. So without input, we conserve energy. All right. So how is this useful for learning dynamics? And and one more point is that this doesn't model dissipation, I guess, is another question. How do we capture drag or kind of friction in this model? So there's a small extension of Hamiltonian dynamics called port Hamiltonian dynamics. So port Hamiltonian models also introduce the ability to either inject new energy or remove energy from the system. So they essentially have a dissipation matrix here called D. So we have, so in general, right, a port Hamiltonian model looks like this, where H is the Hamiltonian, or the total energy, is always positive. J is the skew symmetric matrix, which we said guarantees conservation of energy. D is a symmetric positive semi-definite matrix, which encodes the energy dissipation. And then finally, G is some input gain for the system. Okay, so now if we want to learn the dynamics, instead of using a black box, our idea was to use these port Hamiltonian dynamics. So essentially parameterize some of these things like D or G or the potential energy in the Hamiltonian, and learn neural networks for those as opposed to directly for F as a black box. The main benefit of doing that is that we'll encode the kinematic constraints and we'll encode the energy conservation directly by design. Okay, so we did something like this. So we had 4 neural networks. So one represents the mass or the mass inverse. Another represents the potential energy. A third one, the dissipation. And a fourth one, the input gain. So we're given position and velocity observations. We pass them through these 4 neural networks, which give us the Hamiltonian model. We use the ODE solver forward in time to predict the trajectory going forward. We use the ODE solver backward in time to get the gradients and update the neural networks. So again, what's the benefit of doing this versus just a black box neural net? We guarantee conservation of energy and kinematic constraints by design. So we don't have to infer those from the data. We already have them in the model. Correct, single pass, but yeah, but we do multiple forward, backward as gradient steps. Yeah. That's right. Yeah. So here's so we applied this to a quadrotor system to verify whether this works. So this is just data collection. So human is just flying the robot around. We use motion capture to collect position and orientation and velocity observations, and we train this model. So here's some comparisons between training this versus a black box neural ODE model. So on the left, we checked this energy conservation. So if the green and the red lines are essentially our Hamiltonian type model, while the blue line is a black box model. So on the left, if the input is 0, we would expect these lines to stay constant. But with a black box model, that's not guaranteed. In the middle, we check whether we have the rotation matrix remain on the SO3. So our transpose is identity determinant is 1. So again, with a black box model, you might not guarantee that. And finally, in the third example is convergence over number of training iterations. So you can see that with the Hamiltonian models, the convergence is a lot faster. So you need fewer samples to train the model. So it's more sample efficient. So these are just empirical observations. Yeah, question?
I have to ask, where is the state coming from in supervision and in inference?
Yeah, great question. So for now, we're assuming we observe that directly. So we
estimator or mockup?
Mockup for the data collection, and during deployment, estimator.
And
very good question. Yeah, so we are measuring velocity, and you can estimate from velocity, you can estimate the momentum. So I presented it in terms of momentum, but we can make velocity the input. So you multiply it with the M, which is a neural network, to get the momentum, and from there go on. Yeah, good question.
But shouldn't be the supervision involve a state estimate, which has a noise and the noise?
Yeah, good. Yes, it should. Not considered yet. Or for now, we're assuming we're kind of given the states. Yeah, which I agree with.
Any difference in inference between mockup versus state in inference?
So I'll show you the deployment in a second. Yeah, so when we trained this, we put it on an actual robot. We've used both either motion capture during deployment as well, or MSCKF, like visual inertial odometry. And it works in both cases. I guess the question is how robust is the network to error in the state? But we haven't done anything smart for that. So we just trained with a lot of data and then test. It would be nice to think about some robustness to noise. Okay, so let me show you some examples. Oh yeah, so how do we do control, right? Once we have this model, another side benefit of these poor Hamiltonian models is that the energy or the Hamiltonian can directly be used as a Lyapunov function candidate. So you can use some passivity-based techniques to design a controller rather than maybe solving reinforcement learning or optimal control. So let's say we want to fly the drone to desired position orientation with 0 velocity. If the input is 0, this X star is typically not going to be an equilibrium of our system. So in this energy-based design, the idea is to inject new energy through the input to make X star an equilibrium. So how should you modify the Hamiltonian to have that as a 0? So we can define a new desired Hamiltonian. So the idea is give energy through the input so that the new closed loop system is another Hamiltonian system, which has a new Hamiltonian that's given by our desired one. And the desired Hamiltonian should have a minimum at X star. So if I can reformulate my system into one that has the minimum at the desired state or trajectory, you directly get kind of the control which achieves this, gives you the way of stabilizing at this state. So essentially, we have the actual system on the left here and the desired one on the right. And just by setting the two states equal, we can solve for the input. So there are definitely more sophisticated ways of doing this, but I'm just giving a simple example. So you set these two equal to each other. So as long as we can do like a pseudo inverse on G here, we can get what the policy should be. So depending on the system, the pseudo inverse might not be a great idea. You might need something more complicated. But for example, for a quadrotor, this is not a problem. Depends on how you choose X star. So here are some examples of this now actually working in practice. So this is after we trained the model, we directly deployed this on a quadrotor, and we're able to do trajectory tracking. Even though there are obstacles, we're not sensing them in any way. It's just tracking some desired trajectory. So with this, for example, you can do things like change the dynamics of the robot, like add mass or some other perturbation, and train the model a little bit longer, and you can again deploy the controller right away. So you don't need to like design a new controller for the robot again, right? So if the robot dynamics change, you can reuse this again. So currently we are, yeah. So we used kind of our own collected data, so it wasn't too much. I think training the model also takes like half an hour, I would say, about. So it's not really real time or anything like that. But yeah, we probably used several hours of data. See whether the energy functions that are getting learned there are actually in line with what we would expect from physics model. Yeah, I mean, I think again, by design, your energy will satisfy the conservation. So if your input is 0, they'll be constant. We haven't done anything very smart in terms of checking kind of so some things we observed is that, for example, when we collected velocity measurements, they tended to be quite noisy. So maybe it's related to Kostas's question as well. So we had to do some sort of filtering on this data. If you directly train with the raw data, it wasn't working as well. But that's the only kind of thing I can think of. So right now we are working on trying to do this online. So allow the adaptation to happen in real time. So the question is how to do this fast enough. So we're looking at some low rank model adaptation as we're flying. We've also looked a bit at learning other aspects. So for example, bias for an IMU in VIO. So one nice thing about the IMU, for those of you who know kind of rotation kinematics, you know that you have very nice symmetry, but if you include the IMU bias in the system, that breaks the symmetry. So you cannot use the invariant Kalman filter anymore if the IMU is part of the system. So what we try to do is predict the IMU with a neural network and then do the rotation integration with respecting the symmetry. So I'm going over this kind of quickly. Controller is not learned, yeah. It just uses the Hamiltonian as design.
Then also like a model controller. So in this sense, it's not a limitation because the controller is not
exactly. Yeah, the controller is computed.
It's not elaborate. Right?
Yes. The controller does involve the terms we learned, so it has the mass and the input gain and so on show up in the controller. So those terms are learned, but the control structure is by design.
But during learning in the diagram, you had only the U
coming in. Correct. We directly supervise from states. Yeah, great question. Maybe there's a way to supervise from inputs or something like that.
Propagation through the U to the control equation, right?
That's right. Yeah. So the controller is just designed directly. Yeah. Okay, so this was about robot dynamics modeling. Okay, maybe it was just a single rigid body, and there's more work to be done here. How do we do this for an articulated robot, maybe for a humanoid? But I'll save this for next time I'm giving a talk. So we haven't done that yet, no. So all right, so let's talk about environment modeling next. So we spend a lot of time also doing mapping. So in environment modeling, we assume we have RGB, depth, maybe semantic segmentation as input, and the goal is to produce a map of the environment that maybe captures geometry and semantics, like do we have a fridge or a window or a radiator? So let's look at some common representations. So in 2D, we know the image is king, right? That's the right representation. What happens in 3D? Well, in 3D is a jungle. There's all kinds of representations. So one that we all know is the occupancy map or the occupancy function. So we have a function which gives you -1 in occupied space and 1 in free space, for example, so just binary, and you can construct something like this. More recently, sign distance functions have become quite popular. So what is the sign distance? So instead of just -1 or 1, it tells you the distance to the nearest surface, so minus the distance if you're inside the object or obstacle, and plus the distance if you're outside. So this color here, essentially, the redder it is, the closer you are to the surface. You can also think of something like a NRF or a neuroradiance field, where the input is both position and viewing direction, and the output is volume density and color. So in NRF, instead of 0, 1, it's more of a probabilistic description of space with the density. So if we formalize these functions, now we can think of mapping as a process of learning these from data. So if I can approximate H using data, I have a map. So just very quickly, I'll mention about occupancy functions. You can extend this from binary to multi-class. So you have different categories like chairs and windows and doors. And we've done work on this. So this is an extension of the Octomap paper, in which we store multiple categories per octant and associated with different semantic classes. I'm going over this quickly because I'm going to focus more on the sign distance function part. But we have some work in which we did multi-robit semantic octree mapping, and we have an open source implementation as well. This is in collaboration with VJ and CJ and people who work on DSYST. And this is an example running on UPenn's quadrotors and building an octree here where the colors represent the different classes. Okay, but I'll talk more about the sign distance function estimation now. So again, what is the sign distance, right? So I have this function h. If I query at a point, it gives me the distance to the nearest surface, negative inside, positive outside. It has a lot of applications, so it's used for in graphics. People are using it for manipulation to measure kind of distance in configuration space. It's used for rendering as well. So how do we do sign distance estimation? Again, the idea is we generate a training set, and then we want to train a model of H theta. So we can use either a neural network or some kind of Gaussian process regression. What does the data look like? We assume we have some sort of a distance measurement, so either a LiDAR or a depth camera. If you only have RGB, then you need to estimate those 3D points. But to keep things simple, so let's say we have a LiDAR or a depth camera. So I'm going to get hit points here, these red points in the surfaces of the environment. For each hit point, we can associate kind of a little region around with these green points. And for each green point, I can measure the sign distance from the green point to the place where we hit. So I can build a little data set, right, where the green points are the locations and the distance measurements are the y's. So I have pairs of x and y data like this. And now I can train a model for this. Okay, so how do we do this? So there was a paper called ISDF, which, well, actually, maybe the first one was Deep SDF. So there was a paper which showed that just training a single MLP with this data can reconstruct sign distance function fairly well. A slightly more recent one is ISDF, which does incremental updates and has it together with a SLAM setup. So using a single MLP is nice in terms because it's differentiable and kind of completes missing parts of the scene. But it has limited capacity. So if you start doing it for a large room, it starts to forget parts of the environment and have kind of problems with fine details. It over smooths. So more recently, there are methods that introduce some data structures in the mix. So there's maybe a feature grid which stores features in the environment and then does the MLP reconstruction after that. And these methods give you a much better reconstruction, but they tend to be quite expensive. So you probably wouldn't run something like this on board a quadrotor. So in our work, we kind of try to look a bit at how to do this more efficiently, but still have very accurate reconstruction. Okay, so I'll tell you about MISO. So this stands for multi-resolution submap optimization. So it's our approach. So our idea was to store features in space. So it's multi-resolution because we have two resolutions of these features. We have the coarse ones here in the middle and the fine ones. So we have some sort of a grid of features. We have submaps. So these little squares are different parts of map in the environment. And in each map, we store these features from which we're going to reconstruct the sign distance function. Okay.
Why are they called implicit?
Why are they called implicit? Because the features don't have a direct physical meaning. So they're not distance or anything like that. But we use a neural network to decode them into a distance.
And you still query, right? You query the.
Yeah, so I'll show the architecture now in more detail. Yeah. So let me show you what it looks like. Okay, so we have kind of the road moving around. We have camera observations. Let's say we're observing a point here. We have a little local map we construct, and we discretize this into a grid with maybe several resolutions. So we have the coarse grid and the fine grid. At each blue point here, I store a feature. So actually for distance estimation, this feature doesn't have to be very large. We only use like 4-dimensional features. But if you want to do something fancier, which I'll mention later, like predict semantics or language, you need more. So then if you have a query point, X, as Kostas asked, right? If it's not on the grid, we do interpolation to predict what the feature is at that point. We concatenate the coarse and the fine features into a single feature vector. And we pass this through a neural network decoder, which is just a multi-layer perceptron, and this predicts sign distance. So you can train all right, so how do you train something like this? So you can train the decoder offline over many different scenes and freeze it. And the only thing you need to optimize online is the actual features. So there are two things that need to be learned here: the feature values, F1 and F2, or the features on the grid, and this decoder. The decoder can be pre-trained, while the features need to be optimized online. If you have a new environment, I think you'll get much better results than pre-training those as well. Yeah, so this is very similar to nice SLAM, exactly. You optimize the features every time. Yeah, so I'll say a little more how it compares to nice SLAM soon. Okay, so our multi-resolution grid, again, just a summary of this looks something like this. So we have the features at different levels. We concatenate the levels with this O+ operator. We pass through the MLP. This predicts the SDF. So we can formulate now a SLAM problem, for example, where we're optimizing simultaneously the features. So that's our map, and poses for the camera. So all the poses do is transform the points from the sensor frame to the global frame, because the map is in the global frame and the observations are in the sensor frame. We pass this through the decoder with the features, and we try to minimize error with respect to the measurement. Okay, so one interesting thing we did is, in addition to a decoder, can you have an encoder? So instead of initializing the features randomly, maybe you can initialize them a little more smartly so that they converge quickly. And the fact that we have a hierarchy was also interesting. Like, could we first have a quick coarse model of the map and then refine this into something more precise? So the intuition was that coarse features should give you some information about the finer details. So we looked at let's suppose kind of the only nonlinear thing here was the decoder. So if we make this just a linear function, what happens then? So we looked at the linear case. So let's say the H function is now some linear combination of the features. So we have F1 times J1 transpose F1 plus J2 transpose F2. And suppose we're trying to find what is the optimal choice of F2. So we minimize some squared loss here with respect to F2. If we do this computation, we see that F2 is minus J transpose J, pseudo inverse J. So it's just a linear system solution. So we see that F2 is a function of the residual at level. So the optimal feature choice in level 2 is a linear function of the residual in level 1. So in the case of a linear decoder, you just need a linear transformation. Okay, what happens if the decoder is not linear? Well, we can think of this as, again, some encoder which takes the residual from the previous levels, passes it through an encoder, and produces the features. And now we can also pre-train this encoder offline. All right, so let me summarize what I said. So we have some initial point cloud here. We pass it through an initial encoder, which predicts the features on level 1. We measure the error between the predicted reconstruction from the predicted features and the observations. And we use this residual now to form an encoder for level 2, which predicts the features on level 2. So initializing from the encoder is much faster than optimizing from starting from random features. Yeah. You intend that level 2, the kind of like
finer feature grid actually captures information that doesn't exist. Sorry, the coarser feature grid captures any information that doesn't exist in the finer feature grid. Like, why not? Why should the final decoding process not just rely on the finer feature grid?
Yeah, good question. I actually don't know. Yeah, we're kind of using both. Maybe it can be just the final one.
Where you were going with this was that you intend at test time eventually to sometimes operate from only this coarser.
That's a great question. Yeah, actually, you probably can. Yeah, we didn't consider that. We thought, okay, give all the information to the decoder, but maybe you can do it at the. So the only challenge I see is you want to make the decoder somehow resolution aware, because if you just give it features, it wouldn't know. So you need some sort of positional encoding, but outside of that, it should work. Yeah. So here's a visualization. So if we first train the coarse level, we get like a low prediction like this. And then if we add residuals at the fine level, we get a much more accurate reconstruction. So here's some, so the blue is the errors in the sign distance measurement, and you can measure different kind of functions of sign distance. So that's why we have several channels, but I think just one is enough. So this is sign distance prediction. We predict the first level, we measure the error here, and we feed the residual, the errors to the second level decoder. This is the decoding. Okay, so here's a comparison between MISO, which is our approach. So initialization is just from the encoder. This is after 20 iterations of optimizing the features. The one here is the ISDF, which is a single MLP, and the one on the right is an architecture that uses many points. So it's similar to NiceSlam and to PinSlam, but it's not. I think we implemented something inspired by PinSlam. So this is on another scene. So how does this perform? So with the hierarchical formulation, we can be much faster and we can get slightly better results than some of the baselines. Let me see if I can show you, or maybe let me say one more thing and I'll show you more results. So this was for a single submap, but if we have multiple submaps, we can also align them to get kind of a globally consistent map. I think this is fairly standard in robotics to do submap alignment. The only important or only observation here is that we can do the alignment of level of features now. So we can do a coarse level first, then the fine level, and then finally SDF. So existing work mostly does this at the SDF level directly, which works a lot worse. So let me show you what I mean by alignment. So essentially we have the submaps and we have the features in the different submaps. So you can query feature 1 in submap 1, what is the corresponding feature in submap 2? Because we can do interpolation, I can predict the feature value there, and I can form a little error term here, which is the feature in submap 1 minus the feature in submap 2 obtained by transforming the point from coordinate frame 1 to coordinate frame 2 and querying there. Sorry, I think this should be, yeah, that's right. And we can measure this as an error and optimize with respect to the transformation, so I can estimate the alignment. And we can do this for the coarse level as well. And finally, in the SDF space. So here's an example of what this looks like. So on the top left, we see an alignment in the sequence of coarse, then fine, then SDF. And on the bottom left is kind of a direct SDF alignment, which doesn't work as well. So we compare it against several baselines here, ICP, one of them, and a couple other methods that do this. So this sequential feature-based alignment is pretty reliable. So here's some more qualitative results. So we have on the top is the ground truth. This is reconstruction from our method, and this is ISDF. We run this also in newer college data set, which is real data and relatively large scale. So you can see again SDF reconstruction. So the part that I'm excited about is that, as we said so far, the features were used for SDF, but we can now start to think about the features having more kind of extended meaning. So we asked, can we try to approximate clip or dyno features with this model? So essentially, we get clip features from the images, we project them to 3D, we encode them in the map. So we had to do the encoder and the decoder had to do some compression in the dimension because clip is 700 and 8068 or something like that. So storing so much data was difficult. So we have the latent space we compress to is lower dimensional. We use 64 or 128. We're experimenting with this currently. So this is sort of ongoing work, but this is a PCA visualization of what the features look like. So one thing that's nice is that kind of they're similar on similar objects. And we can now start to think of things like asking the map questions. So you can, if you have clip features, you can ask where is the red bag besides the door. And this will, just by doing cosine similarity in the feature space, you can highlight different regions, or where's the refrigerator besides the sofa. So this is something we are working on currently. And there are a number of other extensions you can think about. This is, again, ongoing work. So how do we deal with dynamics? So this is, again, a PCA visualization of our map. So we're thinking about how to move the features around as objects are moving, or maybe having a map of the robot itself. So we're thinking about having a robot map, so having features on the robot body and have that part of the map. So you can think about kind of correlation between the object features and objects in the environment. Correct, yeah. So on the both on the left and on the right, we're thinking about things moving as well in the feature space. Not right now. Yeah, not right now. Good. Okay, so if we have this map, we can also now start to think about using this as an input to a policy rather than images. So the idea is that we take the image information, we accumulate this in the map, and then we provide the map as an input to the policy rather than the images. What's the benefit of this? I'm bothered that people use images only because they have a limited field of view and they have limited temporal information as well. So if you want to do some longer term tasks, you're going to need a very long sequence of images to do this right. So in robotics, we've always done mapping, and that's the right way of accumulating information. So my goal is to bring maps back into the reinforcement learning loop. So we've tried some preliminary work on this. We trained a transformer on top of our map. So we extract tokens from the map, local and global. We provide this to a transformer policy, and we train this from demonstration. So this is kind of behavior cloning. And we compared this versus image-based policy. So the one on the left is trained with just sequences of images, demonstrations, and behavior cloning. The one on the right is trained with the same way, but we also provide features from the map. And we can show things like, so here the task is for the robot to navigate and pick up an object somewhere further. And we can show that if with image-based things, if the object is not initially in the field of view, it's very hard to learn these kind of search behaviors to find where the object is. While if we have a map, we can do this well. And so we've tested this idea also on a kind of mobile manipulator to do language-based task satisfaction. So like clean up, throw away a coffee cup, or so on the right, you see a visualization of this 3D feature map. It is a projection, again, in PCA. And we have the robot follow the... So I don't think the task execution is not very sophisticated here. I think the interesting part is the building the 3D feature map. And from that, we can correlate with the language and do some instruction following. So this is in collaboration with Xiaolong Wang and also CMU. But a lot of the experiments are on UCSD's campus. Right, so that's it about environment modeling. So last, let's talk about task modeling. So we talked about robot modeling, environment modeling. So let's talk about task modeling finally. So one thing I learned here at UPenn, and the one thing that was very popular when I was starting my PhD, was to use temporal logic to represent tasks. So George and his students, Hadas and Yorgos, had a sequence of papers on temporal logic-based reactive mission planning and motion planning. So what is temporal logic? Let's do a very quick recap. So we have atomic propositions. So those are binary statements about what's true in the environment. For example, the agent is close to a door, or the agent has a key. If we collect a sequence, so then we define a label. So a label is a collection of these atomic propositions. So, for example, here we have an example of a label which is related to 3 propositions. Does the agent have a key? Is the door open? Has the agent reached the goal? So these are like true-false type of statements. And you have a sequence of these labels over time, depending on what's happening in the environment. And you can formulate logic on top, like not and and or, the first order logic, as well as some temporal operators, such as eventually and always and so on. So with these, you can describe fairly complicated behaviors for robots. So temporal logic can also be translated into automata. So for those of you in computer science, you've probably taken some automata classes, maybe with Rajiv. So for example, for LTL, we can get a Buki automaton. So what is a Buki automaton? It has states, has an alphabet, has a transition function, and has accepting states. And essentially, it's like a graph, right, where the state transitions when you observe these atomic propositions. There are many automata, right? Another one is weighted finite automaton. Again, you start with some initial state. You multiply with a matrix A, which depends on the label you observe. And you do this sequentially, and you can predict how the state in this automaton changes. And at some point, you can say, does this satisfy my task or not? So we can think about learning this kind of structure. So I want to think of tasks now as dynamical systems almost, right? So Q here is the state of the task, and the automaton tells us how the state transitions. So this is the model, and we can try to learn this as opposed to encode it or understand it implicitly. So let's suppose we have demonstrations. So we have a sequence of these labels and an observation whether, let's say, S can be, is the task successful or not? 0 or 1 is the simplest observation you can have in an automaton, or you can have some success level, like how did you do on the task, 90%, 80%. Okay, so that's our data. And the question is, can we learn a function now which takes a sequence of these labels over time and predicts the success? So either binary or some real number. So in the literature, there's actually quite a bit of work on this. So one method that I found interesting is this 2014 paper in which they learn a weighted finite automaton using essentially SVD. So they build a Henkel matrix from the labels. So they arrange them all into a big matrix. And then you do so the matrix looks something like this. You have the success rate corresponding to different label sequences here. And then you compute an SVD on this H matrix. And from this, you can reconstruct the A matrices I defined earlier. So these A's here, which correspond to the different symbols in your language. So far, we're kind of considering a finite alphabet. So you can only have 5 different observations, for example. So you compute these 5 different matrices. You start with an initial state. If you multiply with these matrices, you can predict what the value is. Okay, this we can already do. But we know that in practice, we don't have a finite alphabet, right? We have some observations, which are images, very high dimensional. But we can formulate the task in a very similar way, right? We can have observations and success labels and ask, can we learn some function which takes the sequence of observations and predicts success rate of the task? So we try to do this kind of in a naive way, not knowing anything about temporal logic. We can start with a machine learning model, which has an encoder to process the observations, then some sort of a sequence model to store the task state over time, and a decoder to predict the success rate. So it looks something like this. We get observations over time. We encode this into a latent space kind of label observation. We have some sequence model which keeps track of how the task state is evolving. And finally, we have a decoder which predicts, is this a successful task or not? So it's almost like you watch a video and you tell me in the end, did you do this well or not? Like I show you, I made an omelet. Tell me, did I do well or not? Right? So it's like judging the performance. So we did a number of experiments with this kind of model. So we compared this to first directly on Buki automata, where we know what the true automaton is. We gave sequences from an automaton that looks like this, binary sequences. So our model is called Latmos here. It has several variants depending on the sequence model. We used a GRU or a transformer or state space machine, like a Mamba type thing. I don't think the sequence model matters too much. And we compared this versus this Henkel matrix decomposition method I mentioned, and a couple others that are used in the formal methods community. And of course, for cases where the data comes directly from an automaton, our method is comparable, but doesn't do as well as the formal methods ones. But the nice thing is that our method allows kind of now continuous observations or perturbation. If you make the labels a little bit noisier, none of the formal method ones consider that case. While here we just have an encoder, so we can still deal with this. We tried this on a kind of real video data set. So there's this EXO 4D data set where we have videos of tasks, and we need to predict either keyframes, like labeling keyframes, or predicting success. And we compared our method versus some of these large language models, so XClip or Omnivore or Ego VLP. So all of these do predictions pretty much based on a single frame or a short sequence of frames. And they're trying to say, is this successful, or which keyframe is this? In our method, because we have the sequence model, we're kind of accumulating information over longer sequence of frames. So we can do this better. So we're able to get a better success rate in predicting the task. So yeah. Okay, sorry. Yeah, so we start with the image, and we have an encoder which produces some feature. And the feature then goes into a sequence model. And then we have a decoder which just predicts 0 or 1. So here we don't actually have an automaton anymore. It was just inspiration, but we just had a sequence model. Yeah, it uses the visual feature encoding, so like CNN features over time, and we just put them in a sequence model. So it's not, there's no discretization anymore. We kind of use the automaton as inspiration, but we didn't actually implement that exactly. Oh, you can decode at any time. Yeah, good question. Because we decode from the latent state in the sequence model. So you can decode intermediately as well. Yeah, you don't have to wait until the end. Yeah, I think reward models are very much in the same, very similar. That's right. Yeah, so finally, I guess I should also stop maybe. How much time do I have? Okay, yeah. So we can use this for planning as well, which is the part I'm excited about. So this latent state we have in the sequence model can be some sort of a prediction of how well you can satisfy the task. So you can imagine now doing something like task planning, where you use the latent state to predict like a heuristic in A star of how likely is it, if you take different actions, for this to be satisfied. So yeah, I'm going a bit more high level here because not that much time left, but we did these kind of door key environments that I mentioned earlier. So we had examples of satisfying the task. We trained the model to predict task success. And then at different states, we can use the hidden or the latent state in the task to predict success and use this as a heuristic for A star planner. So if we do something like, so we compared doing like a Dijkstra search in this case versus heuristic like A star with heuristic from the learned task model. And we can achieve efficiency that's pretty much comparable to a model which knows the sequence of the operations you need to do, like the demonstrations. Okay, maybe last thing I'll say is we can also use these. Yeah, another example of using this for task planning. So we have a natural language task here. We build a semantic map like the semantic OC3 I mentioned earlier, and we can ask to generate temporal logic from this. So we've formulated temporal logic generation as a code generation task. We observed that language models are not very good at temporal logic synthesis because they haven't seen many examples. but they have a lot of examples from code generation. So we phrased the question as there are, I think I have an example here. So we kind of defined LTL operators. So we said you have an and, you have an or, you have a not, you have an until, you have an eventually. And we asked the LLM to synthesize code which uses these operators. And this works much better than directly asking it to give you temporal logic, because they've seen many examples. If there's a syntax error, we reprompt and say, this is your error. So we could essentially get 100% syntax accuracy. There might still be semantic errors, but syntax we could do much better versus there are several other papers which directly use LLMs to generate temporal logic from natural language. And we can do much better by this kind of code generation approach. So if we can synthesize temporal logic, then we can do task planning. So here's an example of a person speaking to the robot, saying something like visit an umbrella, then a microwave, then a person, and so on. So sequence of objects, something like this. So we translate natural language into temporal logic to an automaton, and then we did task planning with that. You can see the robot on the right executing the task. Okay, I'll just in one slide just highlight a few other things we've worked on. So we have some work on safety, both for manipulation on the top left, kind of how to enforce safety constraints if someone is messing with your robot, or for navigation in the top right. We've done quite a bit of work on mapping at object level as well, in collaboration with VJ and CJ on the bottom left. This is for the thesis project. And we also have some work on multi-robot RL, where the idea is how to decentralize the policy so it doesn't use the states of all the agents. Okay, let's conclude. All right, so what did we say? So modular representations of the robot, the environment, and the task, I think reduce learning complexity. We can use less data and we can encode some guarantees. And they enable unit testing, so I can test my robot model separately from my environment model, separately from my task model, and I think enable generalization. Robot models can be learned as neural ODEs, maybe with a Hamiltonian structure. The environment models can capture multimodal information like semantics and dynamics and topology, and that's useful for task specification and planning. Task specifications, I think, should be viewed as dynamical systems, and we have system identification, so we should be doing a lot more of task identification as opposed to kind of inferring them implicitly. And how about going forward? So I think there's a lot more work on model-based approaches. So I think we can look at more expressive and general models for all of these aspects. And if we have models, we should be doing a lot more of model-based RL, I think. If we have models, we can also get into uncertainty quantification, which I didn't discuss today, but I think is a key problem, because this can give us information about active perception. And yeah, maybe one more thing in terms of future work, I think it's important to start doing online reinforcement learning again, as opposed to this large-scale offline training. I want to see robots learning on the fly, so I'm really looking forward to that. And finally, yeah, distributed formulations of estimation or optimal control, multi-robot things are important, and I expect to see more of this. Thank you very much. It was a great pleasure. I'm happy to take questions.
Hey, thank you for the talk. I have two potentially unrelated questions about the automata inference. The first one is there any motivation for using Buki acceptance conditions? Because I think most things we are interested in are finite words. And then maybe I can ask one question at a time.
Yeah, no. I think I spent a lot of time thinking about Buki automata myself, and nowadays I'm questioning, do we need to know exactly what type of an automaton we have? I think not necessarily. I think the idea of using an automaton is the right one, but what class of automata we use, I'm not so sure. So I definitely don't insist on Buki. As I show, we kind of just use the sequence model to try to approximate what an automaton does. So people who are in computer science working on this might disagree with me, but I think just the part that's inspiring to me is the fact that we have an automaton with a state that changes over time. But which automaton specifically we use, I don't have a strong opinion.
Yeah, then that makes sense. And then my second question is, for this sequence model that you train, do you think there's like potential to distill it down into a symbolic representation that looks like an automaton?
That's a great question. It's not something we've tried, but yeah, I mean, potentially. I don't know if it will be discrete. It was Kostas's question as well. I'm not sure. Yeah. So far we tried like a black box one. So the states were continuous under the hood. And I don't know what the benefit would be, but yes, maybe if you quantize, right, that state, you might start to infer what are some semantically meaningful states for your task.
Yeah, thank you.
Thanks for this great talk, Nikolay. I was curious, like when you are doing this work where you are like using code to represent your automatas. I saw that like most of the models that you were using were like general models. Like these days, like you have like these models are like really good for coding, and I was curious if you guys tried to like use these to see how the performance of your system was.
Oh yeah, great question. No, we use ChatGPT mainly because we have an account for it and we have the API set up already, so it's the least effort. But yeah, I think it would be nice to try other options.
Okay, thank you.
I just had a question about the MISA work. I think maybe I missed some of the details, but for the submap alignment, where I assume you just do something like L2 distance in the latent feature space to do this.
Yeah.
And I'm just curious, like if these latent codes are just decoding to this very low dimensional thing like an SDF, is there potential that the latents, even if they do represent the same SDF, are like actually quite different? And I mean, I believe in your animation, the alignment seems to work well, but yeah, do you have to do anything special to ensure like features do correspond to the right things?
Good question. I mean, I would say ideally we would want the latents to be similar as well, but we didn't do anything to enforce that. So we did measure L2 distance essentially in the coarse feature space, then in the fine, and then in SDF. And this seemed to work well enough. But I think your question is quite interesting when we move to kind of language or vision, where the latent features are much higher dimensional. And so, yeah, I don't have a very good answer. We've played with some stuff like forcing, like using contrastive learning to get features on the same object to be closer to each other and on different objects to be further apart. So you can try something like this, and we're experimenting with this, but I don't have anything conclusive yet whether this helps or makes because it might affect the decoder and encoder models as well. So I don't have a good answer yet. Good question. Yeah.
Thank you.
Hi, thank you for the talk. So I had one quick question about your ODE work at the start. So basically, if during the training stage, the stage where you have to kind of calibrate your M and your I matrices, so how do you reason about what type of maneuvers you need to train on in order to get good coverage
during your Yeah, I didn't mention persistence of excitation. Yeah, you need that, and we didn't encode that formally, I guess. But yes, you need to excite all directions in your model, and we did this heuristically. So essentially, we had kind of a human collect the data or fly the drone to waypoints. So it shows, yeah, we tried to do coverage, but we didn't do it very carefully. I think if you're doing this even on board the robot, I imagine one day, right, if you can do this fast enough on board the robot, it would be really interesting, almost like an active data collection problem, right? You need to make sure you've tried the left turn as well and the right turn as well to collect data. Yeah.
Thank you for the great talk. I was wondering, in the first part of your talk, you described this constrained learning approach for the Hamiltonian model. And you mentioned that for the aerodynamics, we can do this if we consider a single equilibrium, but this is more on the stabilization part. And I was wondering how that extends to tracking, because the simple approach where you like consider different waypoints and all the different equilibria during the mission would require learning a different model, I guess. So
Yeah, great question. Yes, so you can formulate the same thing with a trajectory as opposed to an equilibrium, and the trajectory being the minimum of the energy over time. But then the method I showed for designing the controller was this kind of equating the two sides and setting them equal and finding a pseudo inverse. So it depends a lot on the trajectory you request. So there are states which are not achievable. So for a quadrotor, if you ask it to hover like this, right, so there's something called matching conditions in this design, which you need to guarantee. So if the matching conditions are satisfied, there exists a control input which can achieve it. If they're not, you cannot. So even for quadrotors, I'm sure Alex knows, there is a way to pick, you need to pick the position and orientation in very particular ways for you to be able to stabilize to that. So I think it's a similar, so in the paper we have a bit of discussion on how to do it for tracking, but yeah, formally you need conditions on what your trajectory is. You might not be able to track arbitrary things. Yeah.
Thank you.
I would close with questions. So your argument in favor of modularized system is more, I guess, that you like the modules, you like the explicit formulations, and it's more interpretable. And on the other side, for quite a while, researchers have argued that there is no way to get all the symbols, so why don't we get something end-to-end? But it seems also in looking at your stuff at the very end, that now getting symbols is feasible because we have so good frontier models, and you can get computer verified language in Lean. And so do you think that the signal to symbol gap has been really closed, and there is really no need for end-to-end systems?
Yeah, great question. Okay, so I think that we don't have to have discrete symbols. We discussed that a little bit, but I do think we should have symbols still. So I do think that we can achieve what an end-to-end system would do with a modular design. Maybe with a bit of loss in performance, we gain a lot in terms of checking that the individual modules are correct and training them with much less data. So I think that giving up a little performance for robustness is a good deal, in my opinion. And yeah, and I don't strongly think that symbols have to be discrete necessarily. Like in the past, we've always thought about symbols as discrete, but these models allow us to map to some latent space, which maybe is lower dimensional, but not necessarily discrete.
All right. Let us thank Nikolay again.